Okay, last lecture we have seen first 9 properties of real numbers. Then we started proving theorems one by one. We proved uniqueness of additive and multiplicative identity, uniqueness of additive inverse, multiplicative inverse, left cancellation law of addition we have proved in the end. Right cancellation law of addition would go exactly same. So now we are proving left cancellation law of multiplication. The statement is for every a comma b comma c belonging to R, A is not equal to 0. If a dot b is equal to a dot c, then b is equal to c. And proof. Now you can write the formal proof systematically, but without wasting time, I always, because a is not equal to 0, as a is not equal to 0, M4 gives me a dash belonging to R such that a dash into a is equal to 1. Given a into b is equal to a into c implies a dash into a dot b is equal to a dash into a dot c, which is equal to a dash into a dot b is equal to a dash into a dot c. Now everywhere we can write the reasons. This is 1 into b is equal to 1 into c. This implies b is equal to this. What is the reason for this? Is because M4. What is the reason for this? It distributes. Multiplication distributes. This is definition of multiplication. You can multiply by maybe definition.
Sir, I think that M4 is M3.
M4 is M3.
Multiplicative identity.
A dash into a is equal to 1. Is M4. A into 1 is equal to a is M3. That reminds me that. Is this proof done? Yes. So let us pause. So left cancellation law of multiplication is done, and hence we can declare that right cancellation law of multiplication is also done. Now let me write down the next important theorem, which is annihilation theorem. If A belongs to R, then A into 0 is equal to 0. For every A belonging to R, or if A belongs to R, A into 0 is equal to 0. Maybe today's theorem number 2. I give you 5-10 minutes to complete the proof. Make sure that every step is supported by previously proved or assumed result. You are not using anything which is not being proved yet. There are more than one ways of getting this result, but we can start. What is the shortest method by which we can go about it? Let us try to do it. Okay. Consider A into 0 is equal to a into 0 plus 0. ठीक है, that could be your first step. Then you can write a into this 0 can be written as 0 plus 0. 0, anything plus 0 is the same. A into 0 plus a into 0 is equal to a into 0 plus 0. D, this is equal to left cancellation, law of addition. Therefore, for any real number a, it could be 0 also. So 0 into 0 is also 0. This we have been using several times and is being proved. Everything which is getting multiplied with 0 becomes 0. Annihilation happens. That is why this is the most important theorem amongst the list. Check whether you have understood. There are more, as I said, there are more than. Let A comma B belong to R. If A into B is equal to 0, then at least one of A comma B is 0. Prove this. Proof. If A is equal to 0, by annihilation theorem, zero into B is equal to 0. Hence, if A is equal to 0, theorem proved. Okay. If A is not equal to 0, A into B is equal to 0 is equal to A into 0 by annihilation theorem. 0 is equal to A into 0 and definitely not equal to 0. That is what is the condition for annihilation theorem. No, that is what is not the condition, but that is the condition for left cancellation law of multiplication. This implies B is equal to 0, left cancellation law of multiplication. Hence proved. Correct. Very simple minded. And why it becomes, because you are using previously proved theorem. Therefore, it is 2-liner or 3-liner. If you go back to using, if you want to use A1 to A4, M1 to M4 and D, then the length of the proof will become little longer. It is not that it is incorrect, but it is going to be little longer. Next.
सर माझ्याकडे लाईट गेली आहे, तर मी व्हिडिओ ऑफ ठेवू?
Oh. 0 is its own additive inverse. Next theorem is 0 is its own additive inverse. करो. 0 is its own additive inverse. By A4 there exists 0 dash belonging to R. Such that 0 plus 0 dash is equal to 0. Let A is equal to 0 dash, and by 3 we have A plus 0 is equal to 0, A is equal to A, therefore 0 dash plus 0 is equal to 0 dash. 1 implies 0 is equal to 0 dash. Okay, so more or less what everybody has written is correct. Then I have next theorem. 1 is its own multiplicative inverse. Shall write down the proof very quickly. Majority of the theorems related to multiplication are similar to that of addition. Their proofs also, except some care needs to be taken. Okay. So here one proof. If I want to use M4, then M4 suggests that 1 is not equal to 0 as there exists 1 dash belonging to R such that 1 into 1 dash is equal to 1. Correct? This is by M4. But 1 into 1 dash is equal to 1 dash by M3. 1. Therefore, 1 and 2 imply 1 is equal to 1 dash. Next, let A belong to R. Let A dash be opposite of A. Let A dash be opposite of. Let A double dash be opposite of A dash. Then A is equal to A double dash. Opposite of opposite is original. A plus A dash is equal to A dash plus A is equal to 0 by A4. A dash plus A double dash plus A double dash plus A dash is equal to 0 by A4. Therefore, if we pick these two and use right cancellation law, or you pick these two and left them. Therefore, A double dash plus A dash is equal to A plus A double dash. Implies A double dash is equal to A. Right cancellation law of addition. Opposite of opposite is original. Next, obviously, Next theorem would be reciprocal of reciprocal. But then before that, let us do, let A belong to R such that A is not equal to 0. Let A dash be the reciprocal, and then what you need to make sure that A dash is not equal to 0. So we will do a small theorem first and then you do the similar one. Okay. So let me give you the statement. Let A belong to R such that A is not equal to 0. Let A dash be reciprocal of A. Then A dash is not equal to 0. Hence it has reciprocal. Right? Because if you are going to use argument something like this, then you ensure that A is not equal to 0, but then you need to prove that A dash is also not equal to 0 because you are going to consider A dash as a multiplier. So that is why this theorem. So prove this. If A is R, which is belonging to R, which is not equal to 0, and if it has a reciprocal, then A dash is also not equal to 0. Easy, but okay, it is easy. Proof 1 implies A into A dash is equal to 1. If possible, A dash is equal to 0. Implies by annihilation theorem, A into A dash is equal to 0. Implies 1 is equal to 0. Contradiction. Implies A dash not equal to 0. Hence it has reciprocal. Next theorem. Let A belong to R. A not equal to 0. Let A dash be reciprocal of A. Let A double dash be reciprocal of A dash, then A is equal to A double dash. Now let me directly write the proof because it is very simple without wasting much time. Proof. It is exactly same as earlier. A into A dash is equal to 1. A into A dash is equal to 1 by M4. A double dash into A dash is equal to 1 by M4. Therefore, A is equal to A double dash by right cancellation law of multiplication. I mean, you need to write A dash is not equal to 0 by previously proved theorem. A double dash is not equal to 0 by previously proved theorem. And therefore, we can apply M4 as A dash not equal to 0, as A double dash not equal to 0. Okay. So that is why we get reciprocal of reciprocal is original. Next we get. For every A comma B belonging to R, for every A comma B, opposite of A into B is equal to A into opposite of B is equal to opposite of A into B. Okay. Let us prove one simple result first and then use that here. Two real numbers are opposite of each other if and only if they add up to 0. Proof 1. Let A comma B belong to R. A plus B is equal to 0. By A4, A plus A dash is equal to 0 implies B is equal to A dash. Part 2, if they add up to 0, I have answered. Two real numbers are, let A belong to R. By 4, there exists a dash belonging to R such that A plus A dash is equal to 0. Proved both directions. One is easy, by 4 converse, you have to show that it is opposite. Okay. Using this, can we go back to our required theorem? Consider proof of this. Opposite of A into B plus A into B is equal to B into opposite of A plus B into opposite of plus B into A by what? M1 commutative, which is equal to B into opposite of A plus A by D, which is equal to B into 0 A4, which is equal to 0. Annihilation here. This implies opposite of A into B is equal to A dot B. But opposite of A dot B is is opposite of A dot B. Therefore, by opposite of opposite is original. No. This implies opposite of A dot B is equal to opposite of A dot B. Similarly, equals A into opposite of B. Okay, so this is important. Two opposite real numbers add up to 0. This is important corollary. Next, for every A comma B belonging to R, opposite of A into opposite of B is equal to AB. This is simple. Layer proof. There is a correction. Opposite of A into B is equal to opposite of. Hey, what are we saying? Two numbers, when they add up to 0, they are opposites of each other. Okay, so maybe I should have written it like this. Therefore, opposite of A dot B is opposite of A dot B equals opposite of A dot B. Okay, maybe this is not convincing. So opposite of A dot B is equal to opposite of A dot B. Is that right? That is what we were supposed to prove, no? Yeah. Similarly, opposite of A dot B is equal to A dot opposite of B. Now it is correct. Using this, actually you can prove it in no time. Let me finish it also. Opposite of A into opposite of B is equal to A. So by previously proved theorem, opposite of A into opposite of B is equal to opposite of A into sorry, is equal to, suppose I am using this result, opposite of A into B. So my B is opposite of B. Opposite of A into B is equal to opposite of A into opposite of B. Is that right? Yes. If I use second result, which is A into opposite of B is equal to opposite of A into B. In this, we get opposite of A into opposite of B is equal to opposite of A into B. It is equal to, by previously proved theorem, opposite of opposite is original. Next. Zero does not have reciprocal in R. Impossible. 0 raised to minus 1 is reciprocal of 0. Implies 0 into 0 reciprocal is equal to 1. But by annihilation theorem, 0 into 0 inverse is equal to 0. Implies 1 equals 0. Contradiction. 0 does not have. Okay. Contradiction. Proof. Okay. Now, I don't know what is this theorem number. If you number them from 1, 2, 3, 4, right from beginning,
15th.
this is theorem number 15. So, up to theorem number 15, for all practical purposes, we have only 0, 1 with us as real numbers. We don't know what is true, what is true, we still don't know. Now, these 15 theorems are true for A1 to A4, M1 to M4, and D, whatever you decide. Now, let me show you why we require 3 more properties, because if we define our addition and multiplication like this in the real number system that we have developed so far, this is the definition of addition, this is the definition of multiplication. 0, 1, 0, 1, 0, 1, 0, 1. So we have only 2 real numbers and we would like to define addition and multiplication. So 0, 0, 1, 1, 0, 0, 0, 1. Suppose we define it like this. What do we mean by this? 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 0. Definition of addition. This is definition of multiplication. What do I mean by that? 0 into 0 is equal to 0. 0 into 1 to 0. 1 into 0 is equal to 0. 1 into 1 is equal to 1. Suppose we define our multiplication and addition like this. All A1 to A4, M1 to M4, D. These definitions satisfy. All A1 to A4. So now I will show you how do you check it. Now, suppose I want to check A1. It says A plus B is equal to B plus A. So you choose A is equal to 0. B is equal to say 1. Okay. So 0 plus 1. 0 plus 1 is equal to 1. 1 plus 0. 1 plus 0 is equal to 1. Implies 0 plus 1 is equal to 1 plus 0 as per new definition. Hence, A1 is satisfied. Let us say M3 if I want to. For M3, what do we need? It is multiplicative identity. Let A belong to R. There exists multiplicative identity 1 belong to R such that A into 1 is equal to A. Okay, this is our M3. करेक्ट आहे ना? त्याच्यात अजून काय पाहिजे? M3 मध्ये अजून काय कंडिशन होती? काय एवढंच होतं?
Sir, A is not equal to 0.
A is not equal to 0. ठीक आहे. So now let A is equal to 1.
सर M3 नव्हती ती कंडिशन.
M4 मध्ये
1 is not equal to 0.
here 1 is not equal to 0. Okay. So let A is equal to 1. Then we put it over here. 1 into 1 is equal to 1. Correct. Therefore 1 is multiplicative identity. So M3 goes through. Yes or no? A is equal to 0 घेतला असता. A is equal to second. 0 into 1 is equal to 0. Correct. So 1 is multiplicative identity. It survives for 0 as well as 1, and those are the only two real numbers that we have with us. Now, what I will give you as an assignment is, I have shown you A1 survives, I have shown you M3 survives. You cross check whether A2, A3, A4, M1, M2, M4 and D survives or not. They survive or not. You cross check. Okay, if you cross check, then all 9 properties survive or only 0 and 1. This definition of addition and this multiplication, everybody survives. 0 becomes additive identity, 1 becomes multiplicative identity, and so on. Therefore, by few more definitions like this in addition and multiplication, we really cannot expand our real number set which we wish to, and therefore we have to assume few more properties. We assume that there exists set of sets P and N of real numbers such that set of real number is P union N union 0, where they are distinct, I mean disjoint. Nothing is common between these three. Their intersection is empty. P and N are related to both addition and multiplication as follows. O1 for every A comma B belonging to P, A plus B belongs to P. O2 for every A comma B belonging to P, A into B belongs to P. And O3 says for every A belonging to R, A not equal to 0, A comma opposite of A for every A belonging to R, A not equal to 0, A or opposite A and opposite of A are distinct, and exactly one of A comma opposite of A belong to P. Now all these O1, O2, O3s are made considering P as important. P here, and P here. That means they are, eventually it becomes set of positive real numbers, but at the moment we are considering it as P only. These are ordering properties. Therefore O1, O2, O3, ordering properties. They will provide us some order. Okay. If we assume these three, then we have a few more theorems to prove. Say for example, 1 belongs to P theorem. Because we have only two real numbers with us, we need to identify, out of which 0 is known. 0 is sitting here. Therefore, the other real number that we have is 1, and we have to prove that it belongs to P. Clear proof? Proof. If possible, let 1 belong to N. By O3, opposite of 1 belongs to P, correct? By O2, opposite of 1 into opposite of 1 belongs to P, but by previously proved theorem, which we proved just now, opposite of A into opposite of B is equal to AB. Opposite of 1 into opposite of 1 is equal to 1 into 1 is equal to 1 belongs to P 1, 2. 1 and 2 contradict each other. Therefore, 1 belongs to P. Correct? Yes or no? Easy. Now, what is 1 plus 1? If possible, 1 plus 1 belong to is equal to 0. Contradiction O1. Because 1 is positive, 1 plus 1 must belong to positive, but 1 plus 1 is 0. Contradiction to O1. If possible, 1 plus 1 is equal to 1 is equal to 1 plus 0 by A3 implies 1 is equal to 0. Contradiction. By left cancellation, law of addition. Therefore, 1 plus 1 cannot be 0. 1 plus 1 cannot be 1. And therefore, because of this O1, O2 now, O1, O2, O3, we are forced to name 1 plus 1 is new real number called 2. And hence we got 2 with us. This is the third real number that we have. And hence we have 3, 4, 5, 6. Hence we have minus 1, minus 2, minus 3, minus 4 by similar. Because if we have 2, then by A4 there exists opposite number. If we have 1, then there exists opposite number by A4. And hence we got all integers at the moment. But then we got rationals also, because if 2 is a real number, then we have a reciprocal 1 upon 2 also a real number. We have reciprocal, so we have everything with us now. We have the entire real numbers with us, entire real number line with us because of this breakthrough So you make a note of this, what I am saying.